Welcome to week 7. Today we will discuss solid mechanics. Basically, we'll discuss two questions, previous year gate questions, that is one related with volumetric strain and the other one with principal stresses. And then we are going to solve two more questions additionally related to stress and strains using principal stress and strain analysis. Okay, first question. GATE 2016 Set 1 question number 31. An elastic isotropic body is in a hydrostatic state of stress as shown in the figure. For no change in the volume to occur, what should be the Poisson ratio? We are given a cube or a body, and we are given that it is in hydrostatic state. Basically, it is submerged in some kind of liquid. One thing to note in that case is all the pressures from all the directions is going to be equal. So sigma x is equal to sigma y is equal to sigma z is equal to sigma. Okay. Now we know this, and we are given another information that there is no change in the volume. That means delta V is equal to 0. That means volumetric strain is also is equal to 0. Now how do we write volumetric strain? So if we have forces in three directions, from three directions, we can sum up the strain in each of these three directions, and we can to get the volumetric strain, we can sum up the strain in each of these three mutually perpendicular directions, and we can get the volumetric strain. So for our case, it is going to be epsilon x, epsilon y, epsilon z, right? Okay, so let's try to write what is the strain caused in the body in each of the directions, so x, y, z, by the stress in x direction, that is sigma x. So in x direction, so this is by sigma x. So in x direction, it will be sigma x by E. Because it is tensile, it will be positive. In y direction, because of this stress in x direction, it will be minus mu sigma x by E. In z direction, again it is mutually perpendicular, so it will be minus nu x by. Similarly, because of sigma y and sigma z, so let me just do this so you can read the full question. Similarly, in from y, the stress in y direction, the strain in y will be like this, and the stress in z direction, stress in z, it will be like this, and their corresponding strains in the perpendicular directions will be given by using the Poisson ratio, and negative direction, because when we stretch a body in here to conserve the mass, this portion kind of shrinks, so the strain in other perpendicular directions is negative. This should be sigma. Yeah. So this is how we can write the strain in all the three directions, and when we add these, we can get the strain for the volume. So the volumetric strain is the addition of all these things. So let's do that. So we can add up all the x, and we will be left with this. We can add up all the y, and we'll be left with means y means, when I say y means sigma x and sigma y. not the strains. And we'll be left with this. And finally, we have something like sigma x plus sigma y plus sigma z. Here, something like this. What is given to us is that this volumetric strain is 0. Since this body is in hydrostatic state and the stress applied by the fluid which inside which this body is submerged cannot be 0, it's not 0, we have to put 1 minus 2 nu is equal to 0, which gives us nu is equal to 0.5. So the question that is asking us what Poisson ratio should a body possess such that when it is in hydrostatic state then there is no volumetric strain. The answer to that question is 0.5. This was a simple enough question. We can get the volumetric strain using our normal concept of lateral strain and transverse strain by adding the strains in the x direction, y direction and z direction. I have added them a little differently. I have added them through just a minute, in this way so that it is easier for me to add. You can do in this way also, and you can do in this way also, and you can again rearrange. And after simplification, we are left with nu is equal to 0.5. Okay. Is there any doubt in this question? Sir, can you please discuss isotropic? So, what is isotropic? Let's say we have. Okay, let's ask. How can you define isotropy, Shailene? What do you think? How should we define isotropy? So in groundwater, actually, it is used very often that you will be given one governing equation, and then you have to transform the governing equation for homogeneous condition and isotropic condition. What do you think isotropy is? Okay, maybe you don't have the idea, so we'll discuss this here. But I would have preferred if you could just say what vaguely do you think isotropy should represent? Okay, isotropy is one thing. Let's start with anisotropy, right? Anisotropy means that if I am at one point inside space, right? I am at one point inside space, and uh, let's say this is a soil sample, right? Soil sample, a control volume for our soil. When I move in x direction, when I move in y direction, when I move in z direction, in this particular point, and let's for the property which we are going to discuss, let's take conductivity. Hmm. So anisotropy means that if I move from this point in x direction, y direction, z direction, or any other direction for that matter, my conductivity changes. My conductivity from this point, if I am moving to any other point, it is changing. It is different for this direction. It is different for this direction, different for this direction, different for this direction. This is what anisotropy means. So isotropy means that my conductivity for all the directions from this point will not change. This will be equal to K, this will be equal to K, this will be equal to K, everything is equal to K. That is the meaning of isotropy. But let's say I have 2 points let's take a bigger box this time, and let's say I have 2 points inside this box. One point is here and one point is here. So this box is isotropic. uh, and we have this point 1 and point 2, and this point is isotropic, so we have k1 in all the directions and we have k2 in all the directions. So what do you think? K1 will be equal to k2 or k1 will not be equal to k2? uh, direction only. So what do you think is the answer for this question, A or B? B, K1 will not be equal to K2. Correct. So I think you have a pretty good understanding of isotropy. That isotropy means from one point, if we go in some direction, the property is not going to change. But if we go to some other point, the property value will change. If I were to say that K1 is equal to K2, that would mean that this box is not only isotropic but also homogeneous. Okay. Okay. Did you understand isotropy now? Okay. Let's go to the next question. This question looks scary, but when we start solving it, it is going to be very simple. For the plane stress situation shown in the figure, the maximum shear stress at the plane on which it acts are. So this is the plane stress. It is given to us. Sigma x and sigma y are both equal in magnitude and they both are pointing outwards, so they both are tensile, so positive. And there is no planar shear stress apparently that we can see on this plane, so tau xy is 0. And we are asked what is the maximum shear stress and the plane on which it acts. What can be the maximum shear stress in the plane on which it acts? So first we'll write the equation for stress and shear stress at any plane which is making an angle theta with x-axis. So this is our x, the plane on which sigma x is occurring perpendicularly, and let's take a plane which is making an angle theta anti-clockwise, right? So let's write the equation for stress at this plane. So this is also a good refresher. If you can write it before me and not in the chat, if in a notebook or something, it will be better, like a reminder. So it will be sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Correct? And tau will be minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Is that fine? Okay. Now let's substitute the values. We are interested only in shear stress, so we will write only tau. Tau will be minus sigma x 50, sigma y 50 by 2 sine 2 theta, tau x 0, cos 2 theta, 0, 0, tau is always 0. So from this equation, what do we find is that the shear stress is always 0 no matter the value of theta. So the answer to this question, that is the maximum shear stress and the plane on which it acts is 0, and it is max, since it is 0 everywhere, it is 0 at it is maximum at all the orientations. Okay, you can also use one standard equation that probably you are already aware of, that is sigma x minus sigma y by 2 square plus tau xy square. That gives us the maximum shear stress. If you use this also, you are going to get the same answer, that is the maximum shear stress is 0. Okay, simple enough question. Now we move on to the, if you have any doubt in this question, you can ask, otherwise we'll move on to the other questions. Okay, so we have more interesting questions here. So this is a nice question where we have to calculate so many things. So it will act as a nice revision mechanism. The strain measurements from a triangular strain rosette, sorry, epsilon 0 is 600 into 10 power minus 6, epsilon 45 is 500 into 10 power minus 6, and epsilon 90 is 200 into 10 power minus 6. Find the magnitude and direction of principal strain. Magnitude and direction of principal strain if modulus of elasticity is 2 into 10 power 5 Newton per mm square and Poisson's ratio is 0.3. Okay. So we are given that the strain in three directions is 600, 500 and 200, and then we are asked what is the principal strain's magnitude and direction. So what we have to first of all understand here is, let's draw the respective stress diagram. Let's say this oh, and also we have to find principal stresses. So anyhow, let's draw the stress diagram. So let's say this is sigma x, sigma y, sigma x, sigma y. We are given that this is sigma x, this is sigma y. So you can consider this as corresponding to epsilon 0 and epsilon 90, right? And then we are given epsilon 45. So it will be for a plane that is making 45 degree with this x1, right? Now we are given something which is related to stress. We are given, let's say, we are given this stress. What often, a mistake we can make is we can see that, okay, we have one strain here, we have one strain here. Let's to find the magnitude, we know this formula 1, 2 is actually epsilon x square x, sorry, epsilon x plus epsilon y by 2 and plus minus root under epsilon x minus epsilon y by 2 square plus phi xy by 2 square. This formula we can, immediately this formula comes to mind and we say, okay, there is no shear strain it is given to us, so we can just assume it as 0. But this 45 epsilon 45 that is given to us, it is given to determine this phi xy, that is the shear stress acting or the shear strain acting on the sides. So it is given to us to determine this. tau xy or correspondingly phi xy. So what we are going to do, we are going to say sigma x or epsilon x is 600. I'm going to ignore this 10 power minus 6 because later on only it is going to be significant. Otherwise, for the rest of the calculations, it is going to get cancelled. And epsilon y is 200, and epsilon at some angle 45 degrees is 500. And using this, we are going to identify phi xy. So if you remember the equation, we have epsilon at any angle is epsilon x plus epsilon y by 2 plus epsilon x minus epsilon y by 2, sorry, cos of 2 theta plus phi xy by 2 sine of 2 theta. And when you put in the values, 500 is equal to, what about here? It will be 400 plus, so theta is 45 degrees, so 2 theta is 90, so this automatically becomes 0, we don't need to compute that, and we have, and this becomes 1, phi xy by 2. So what this gives us is phi xy is not 0, in fact it is 200, and then into 10 power minus 6 is already there, that we have for every value. Okay, now that we know these things, we can go on and proceed and calculate our principal strains. Okay, is there any doubt here till here? Yes, Mukesh. Oh no, okay. So before we go on to calculate principal magnitude, let's calculate the direction. So what is actually direction of principal strain or principal stress? It is the plane where we don't have any shear stress, right? So what is the formula for shear? We have actually written here for the, for the tensile or the compressive stress, but we have not written for the shear. So let's write for the shear phi xy dash, that it is going to be epsilon x minus epsilon y by 2 sine 2 theta plus phi xy by 2 cos 2 theta. And when we put this equal to 0, we get our theta, which is corresponding to the principal axis for strain. Okay, so now let's calculate that. We have tan 2 theta is equal to phi xy divided by epsilon x minus epsilon y. And when you calculate this, what you will get is tan 2 theta is equal to 200 divided by 400, that is 1 by 2. Can you now tell me what is the value of 2 theta? So tan inverse 1 by 2 in degrees. I want in degrees. Can anyone calculate and tell me? Okay, so I have also some answer here. 13.2 is theta, yes, and it is 26.56, and theta is 13.28 degrees. Now this is one theta, another theta will be plus 90, that will be 103.28 degrees. So remember to give two thetas or check for the other theta if you are checking in MCQ. There can be one option only, that is this. If they want to make our life difficult, they can give this option and not even include this option in our MCQs. So always check for the value which is plus 90 also. Okay, so we know this now. We know the location of principal strain. Now let's find out the magnitude. So the magnitude is epsilon 1 will be epsilon x plus epsilon y by 2 plus root under epsilon x minus epsilon y by 2 square plus phi xy by 2 square. So if we calculate this, we'll get the value. So basically, let's write plus minus here, and then finally we'll write the epsilon 1 and epsilon 2. So we have here 400 plus minus root under 200 square plus 100 square. This is 400 plus minus 223.6. Right, so this is 623.6 Newton per mm square, and then when we subtract, it is going to be 176.4 Newton per mm square. Oh, sorry, my God. Yeah, I get so, always we do this for stress. That's why I was going for stress only. But this is strain, and that doesn't have any unit. So 10 power minus 6 and 10 power minus 6, that is coming from the question itself. So this is the strain, principal strain. I hope you are also getting this same. Okay, if you are getting different, then please let me know. Now, the last part of this question. So we have the principal strains. Now we have to get the principal stresses, that is sigma 1 and sigma 2. Now we need, when we are calculating the principal stress, we need to keep in mind of this 10 power minus 6, and we have to use our modulus of elasticity. Let me write that here. So modulus of elasticity is 2 into 10 power 5 Newton per Newton per mm square. 2 into 10 power 5 Newton per mm square. One more thing, this 2 into the Newton per mm square can also be written. I think you all must be aware of this, but just keep in mind that Newton per mm square is also written as megapascal. That is nothing but 10 power 6 Newton per meter square. When you write it like this, it is very obvious, but many of the times we can save 1 or 2 seconds in each question if we just remember that Newton per mm square is megapascal. Okay, just a side note. Now let's try to get the principal stresses. So there is a formula for this. Usually I don't like remembering formulas, but some of them we have to remember. So this is the formula for the major principal stress, and this is the formula for the minor principal stress. Notice that epsilon is multiplied with the minor for major, and epsilon is multiplied with the major for the minor stress. So let's put in the values and see what do we get. Sorry, Poisson ratio is also given to us 0.3. So nu is 0.3, and 1 minus nu square is going to be 0.09, and 1 minus 0.09 is going to be 0.91, and so epsilon 1, that is 623.6 plus 0.3 into 176.4 into 10 power minus 6. Similarly, I can just write here also, and then probably you guys can calculate and tell me what is the principal stress. Okay, now can you guys tell me what is sigma 1 and sigma 2? So we have here 2 by 9.1, we can say, by summarizing all these things. and 623.6 plus 0.3 into 176, that is 52.92. This will give us, let me check, someone messaged. Okay, no, this is old message. So we have sigma 1 as 148.68 megapascal, and sigma 2 is plus 0.3 into 6, 23.6, 187. 187.0, and sigma 2 we have as 79.88 megapascal. Okay, yeah. So I hope you are also getting the same. Uh, can you guys tell me if you are getting the same or different? Okay, I assume you are getting the same. So is there any doubt in this question? We have solved a question which actually talks about lot about the principal stress and strains. So I think this covers the principal stress and strains, how they are used. There is one more question that in which we are going to see how it is used in beams. You know, when you are given some loading on the beam, and when that is when we are covered with, when we solve that, I think it will cover the whole idea of whole concept of the principal stress and strains in a plane in 2D. Okay, so if there is no doubt in this question, we'll go to the next question. Hmm. So in this question, we are also going to use a concept, that is when you are given a load, then what is the shear force in this one location in the cross section. So we'll touch upon that also a little bit, but main focus is on the analysis of principal strains only. Okay. A horizontal steel cantilever is fixed at end A and its free end B supports a vertical load of 6000 kg. The cross section of the cantilever is rectangular, 3 cm wide and 12 cm deep. AB is 30 cm. That is the length, yeah, that is the length. Calculate the magnitude, nature, and direction of principal stresses at the end A, 2 cm above the neutral axis. That is, neutral axis is the center. When we have a beam which is, perfectly symmetrical, the neutral axis coincides with the uh, center of the half of the length or half of the width. When we have something like a T beam, then neutral axis will shift somewhere above. Okay. So we have to identify the magnitude, the nature, and the direction of principal stresses at end A, 2 centimeter above the neutral axis at this point P. Okay, so what do we need to find? We need to find sigma 1 and sigma 2. And to find that, we need to find sigma x, sigma y, and tau xy. Okay. See, for sigma 1 and sigma 2, we don't need to worry about the angle, or the, not the angle, but the positive or negative, the compressive or tensile nature of this shear stress. But No, not compressive or tensile, but whether it is positive or negative. But when we are asked in this question, magnitude nature also, then we have to talk about that. And for that only one good concept we'll use. So let's first deal with the easy things. That is, let's first calculate the momentum at this point, at this end A, and the shear force. So the bending moment diagram should be pretty simple. We have a normal cantilever beam and it is loaded by 6000 kg. That will be 6000 into 10 Newton weight. So 60 kilonewton we can say. This 10 is nothing but G, that is 9.81 usually, but we'll take 10 for our simplicity. And it is also given to us here. So we have 60 kilonewton and the length is 0.3. So the momentum M at A is going to be 60 into 0.3 kilonewton meter. That is 18 kilonewton meter. And what about the shear force diagram? Shear force diagram is going to be the reaction force. So this is 60 kilonewton. The reaction force at RA, it's upward and the magnitude is 60 kilonewton. So the shear force diagram, momentum diagram first of all is going to be like this. So we have this kind of momentum here. So the opposing momentum will be like this. So we have momentum diagram like this, and the shear force diagram is like this. So both are positive. 60 kilonewton and going from 0 to 18 kilonewton per meter. See, this positive shear force is going to be useful when we are trying to decide the sign for our tau. Magnitude is going to be fine, but the sign, the nature for tau, for that this shear force positive is going to be important. See, I hope you guys remember that when we are deciding in a beam, this is the positive. If the momentum is like this, then it is going to be considered positive for momentum. And when the shear force is upwards, it is going to be considered, when shear force is upwards on the left side and downwards on the right side, it is going to be considered positive. I hope you remember this simple thing. If you don't remember, just sign convention for momentum and shear force, you can note this down. Okay, now we have shear force and momentum. Now what do we use? What should we use? Let me write here. Hmm. See, when we have a cantilever beam and we are loading it on the side, it is going to bend like this. What will happen is, let's say this is the neutral axis where there is no tension and no compression. Whatever the fibers are there below this neutral axis, they will be under compression. They are being pushed together, right? Because this length is getting shortened. Now the fibers that are above the neutral axis, they are being pulled together, pulled from each other. So they will be under tension. They will develop a tensile stress and the bottom will develop a compressive stress. So the point P that is given to us, that is 2 centimeters above the principal axis or the neutral axis, it is going to develop tensile stress. And how do we calculate that? Sigma by y is equal to m by I is equal to E by R. I hope you remember this equation where R is the radius of curvature, but we don't need this part, so we are going to let it go. And I is nothing but the moment of inertia of this plane cross section of the beam from the neutral axis, right? So I will be, let's say if this is B and the width is B and the depth is D and this is the neutral axis, it is going to be the moment of inertia about the uh, neutral axis. Now can you guys tell me what is the moment of inertia of a rectangle? Because this is center, so this is d by 2.
Yes, BD cube by 12.
Correct. Right. So this is BD cube by 12. For us, B is nothing but 30 mm, yeah, 30 mm, and D is nothing but 120 mm. So what will be I? It will be 30 into 120. Is it 120? Let me just check once. Yeah, 120. 120 cube divided by 12 in mm to the power 4. So what is this value? Can anyone tell me? Let me rearrange the stuff till that. Okay. So 12 cube in 30, 30 into 12 cube, that is 1728, or 12 square itself. We can delete the 112. 144 into 10 power 3. So it is 4.32 into 10 power 5. Is this correct? Or 10 power 6? Yeah, I think it is 10 power 6. Can anyone confirm whether this is the moment of inertia? Mm power 4.
Yes, sir, it is.
Okay, thank you. Thank you, Mutish. Yeah, now we have momentum, that is 18 into 10 power 6. Let's try to keep them in the same unit range. We have moment of inertia, momentum. What is this y now? Y is nothing but the distance from the neutral axis of the point where we are interested to find the stress. Where are we interested actually in this question? We are interested in 2 centimeter or 20 mm above the neutral axis. So for our case, y is going to be 20 mm. Putting these things into this equation, we can easily calculate our sigma. So I'm just going to write it here. If you guys can tell me what is the sigma, it will be great. So this is Newton. Oh, my apologies. This is Newton mm. Newton mm into mm divided by mm power 4. So the unit is Newton per mm square, that is megapascal. And the value is
83.33.
correct. 83.33 megapascal Newton per mm square. Okay, so this is our normal conventional stress. What about shear stress? So if you remember this concept of calculating shear stress, which involves, so if you want shear stress at this point, that is some distance y above your neutral axis, then you have to calculate the area of the portion that is above your this point, and you have to calculate the centroid of the area, distance of the centroid of the area above the neutral axis. So that formula is tau by sorry tau by y bar is equal to the shear force at this what at the point of which this is cross section, and the area which is shaded here or highlighted here, divided by I, that is the planar moment of inertia, and by B. What is B? B is the width of this cross section at this particular point. So this distance y above, whatever the width is, that is B. So for our case, it is uniform, so we don't need to worry about that. Now we will get the value of tau solving this equation. But one thing you have to remember, that sign convention we have to use little differently here. So what we have to remember is, when the shear force, this is the shear force acting on the body, is positive, which is actually in this case it is positive, then the response shear stress that is going to be developed is going to be negative. So you can simply either put minus sign here in your expression, or what you can do is you can uh, try to just calculate the magnitude and always check whether the shear force acting at that particular point is positive or negative. So I don't usually like to put here the minus sign, otherwise it can be confusing sometime when I actually have the shear stress as minus or something. So the shear force is minus. So I just try to remember, when the shear force is positive, I need to put my tau as negative. Okay, now let's calculate the different components. We have shear force as 60 kilonewton, so 60,000 Newton. The area, so let's write all the components. We have this as 30 mm, and this whole thing is 120 mm. So the half of it is going to be 60 mm. And what we were told? We were told that, just a minute, sorry. Yeah, we were told that this point is 20 mm above the neutral axis. So this is 20 mm. So this remaining portion is going to be 40 mm. So the area of this particular portion above the point of interest is 30 into 40 mm square. I is the same that we calculated earlier. B is uniform, so we don't need to worry about that. Y bar, that is the centroid of this particular area above the neutral axis, is going to be 20 plus, since again this is symmetric, simple to solve, 40 by 2, that is 40 mm. Now let's put all these things into the formula. We have tau by y bar is equal to 60,000 into 30 into 40 divided by 4.32 into 10 power 6 into 30. So we can actually cancel 30 here. 6 into 10 power 1 2 3 4 5 6, 10 power 6 into 16 divided by 4.32 into 10 power 6. This and this get cancelled. We can now write 96 divided by 4.32. So what is the value of tau? It is 4.96 divided by 22.22.
22.22.
Yes, correct. So I am also getting 22.22, and we have to remember here to put the negative sign. So this is compressive shear stress, if you want to say, and we have sigma. Now see, we have put the load only from the top. So let's try to visualize this. Okay, so I don't have space here. Let's see if we can write here. Okay, yeah, we can write. So let's try to visualize this. This was our beam. This was our beam in 3D. We put a very heavy load here, which bent the beam in this way. Right? This is the bent beam. But the stress that we have developed here is, one is the shear stress and one is the tension stress. We have only developed stresses in like the shear in this direction, which is going to be counteractive. Let's say it is going to develop like this, and we have developed the tensile stress in this direction, but we don't have any stress in y. This is equal to 0, and when it is not going to be equal to 0, that you have to kind of imagine when we are going to apply some force from the left side also. So there are going to be some questions where we are going to apply some force from the left side also, and in that case our sigma y also is not going to be 0. Further, in those cases we have to actually account for a resultant shear force here, and that is going to change our sigma, sorry, tau xy also. But for this case, since we are not applying any forces here, there is no stress developed in the perpendicular direction, like that is here on this particular side. So our sigma y is 0. Now that we know that our sigma x is 83.33 MPa, tau is minus 22.22 MPa, and sigma y is 0 MPa, we can easily calculate our principal stress. Is that clear? So let's write.
Yes.
So let's write the formula for major and minor, and in the end we can write the values. So this is our 83.33 divided by 2 plus minus again 83.33 divided by 2 square plus uh, plus or minus, it doesn't matter here, so 22.22 square. So this will give us our sigma 1 and sigma 2 as let me just calculate. 88.88 Newton per mm square and minus 5.53 Newton per mm square. Are you also getting the same answer?
Yes, sir.
Okay. Okay, so that is all for today's session. Thank you for the session, and have a nice week. We'll meet again on weekend.